Alright, welcome to the first edition of How Will This Kill Me? It's a series where we'll be looking at various toxic chemicals and seeing how they kill you at the chemical level, step by step. Exactly what's happening as you get killed. Okay, so this molecule right here is Sarin Gas. You may have heard of it. It's allegedly used by Assad's forces in the civil war against rebel-held territories. Some loony Japanese cult let some go on the subway in Tokyo and killed a bunch of people. So what makes this super dangerous? In terms of toxicity, it's about 26 times as toxic as cyanide. So a very, very small amount will kill you, and moreover, it's very volatile, i.e. it evaporates very quickly and spreads out very quickly. So those two factors combined make it very dangerous. So what kind of molecule is this? It's what's called an organophosphate. So it's a phosphate bound to some carbons, and it interacts with an enzyme called acetylcholinesterase, which is this big guy right here. We'll talk about him later. And specifically what it does is it inhibits acetylcholinesterase irreversibly. So normally, what acetylcholinesterase is doing is it's taking care of this guy, which is acetylcholine. This is a neurotransmitter. And in particular, it's the neurotransmitter that's present in neuromuscular junctions, which tells your muscles to activate, basically. When this is released, your muscles contract. When it's degraded, your muscles cease to contract, they relax. And the thing that degrades it is this enzyme, acetylcholinesterase, this big globby thing right here, again, not the scale. And what this does is it basically just cuts this bond right here. This is what's called acetyl group leaves as acetic acid, and this choline just gets recycled, and you're all good. So let's look at what happens normally, what happens in the when you're not getting killed by sarin. What happens? Okay, so what are these guys down here? This is the active site of the enzyme, right? Okay, so we're going to look at this enzyme again. Right here, this red, this is the active site. This is where the acetylcholine goes, and it reacts right here with these three amino acids right here. These are commonly referred to as a catalytic triad. You see them together in all kinds of different enzymes. Really common. This is glutamate. This is histidine, and this is serine. And that sounds a lot like sarin. So I'm gonna try to speak clearly so you guys know the difference. So what happens here? Okay, in a chemical level, what's happening when this enzyme does its magic? Okay, so first off, the whole idea here is to get this oxygen here to bind here, so this bond can be cleaved. So with that in mind, what happens is this negative charge is going to steal the hydrogen from this nitrogen, and then basically what that'll do is it'll push the electron density, push the electrons right onto this nitrogen, and this nitrogen will become negatively charged, and that'll mean it'll really want to grab this hydrogen here. In fact, it'll grab it with much better affinity than this oxygen here will. And so what you'll end up with is this, right? So this hydrogen has been successfully grabbed by this nitrogen. Now this oxygen has a nice negative charge here, which is what we wanted. So the next step is actually getting this cleaved, getting this bond cleaved right here. So how do we do that? So we have this negative charge. Where's it gonna actually interact? So this carbon right here, it turns out, is actually, it's partially positive. Why? Because each of these oxygen is really electronegative, which means it really, really wants to grab electrons. So it's sucking away the electrons that this carbon has and leaving it sort of unshielded, leaving it positive, and leaving it vulnerable to a negative charge like this to come in and form a bond right here. Carbon can't form 5 bonds, though. As you see, if we just drew a bond here, the carbon would have 5, so that's not going to work. So what's going to happen is these electrons are going to go all the way up to the oxygen. Oxygen going to be negatively charged, going to have a negative charge up here, and we're going to have a covalent bond between this carbon and this oxygen. And now you see the acetylcholine is now fully attached to the enzyme. It's covalently bonded to the enzyme. Boom, 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 like that. So what's the next step? So what's going to happen is this charge is going to come off here, and this bond is going to break, like here. And this works because this oxygen is really electronegative. It wants to grab these electrons, and we form a... I'll show you what we form, actually. Form a nice, stable kind of acetate. This oxygen is negative for a little bit, and then water, there's water all around here, so it'll just grab a hydrogen from the water. And this is now choline, which can go and do choline stuff and get recycled. And this is an acetyl group, and we'll deal with that in a second. So what happens to this acetyl group? Okay, so just any old water, dihydrogen monoxide, is going to come along. It's going to attack just like before. So there are actually 2 lone pairs on this oxygen, which means it can actually, again, with this partially positively charged carbon, just like before, these electrons can come in. This will come up, sort of like this. I'll just draw it out. Why not? And then you'll have and just like last time, this negative charge will come down, and this bond will break. Yeah, and you'll end up with acetic acid coming off, which is going to be the end result of this. This oxygen will grab the hydrogen back from this, and the enzyme will be rejuvenated to its original state. Not quite, as I've drawn it right here, but like... close enough. There we go. So that's all well and good. So that's what happens normally when this enzyme is functioning correctly, when you're not being killed by sarin gas. That's what happens. You get this choline, and you get this acetic acid, and everyone's happy. The enzyme's back where it started, everyone's happy. So what happens when you inhale some sarin? Okay, we're back to the catalytic triad of our 3 amino acids. Only this time we've got this little guy here instead of acetylcholine. What's going to happen? Well, just like last time, we're going to have our negative charge in the oxygen. That's not the right arrow. Let's try and use a sensible arrow. There we go. Like that. Just like last time, the phosphates, this is too many bonds for phosphate, so this is going to go up. We're going to have a negative charge on the oxygen, and we're going to have a covalent bond to the rest of the enzyme. Now, if you'll recall last time what happened when this negative charge came down, this bond broke. But actually, we have a weaker bond here. That's basically the entire crux of this molecule. Is when this negative charge comes down, instead of this bond breaking, this bond is going to break. This PF bond is really weak, and this fluorine is just going to fly off and do its own thing. And let me see if I drew this. Yeah, go me, I guess. Yeah, the fluorine went away, we got this double bond here, and it's now covalently bonded to the enzyme. Now the problem is, when water tries to come in, it's not going to be able to break this bond here, this phosphate-oxygen bond, and get the enzyme back to where it started. And you can kind of see why, actually. I've kind of illustrated this here. So I've just rearranged the atoms a little bit. I'm going to compare it to this molecule, which you may recognize as DNA. These are the nucleotides, and they're linked by a phosphodiester bond. Let's just compare this real quick. Not quite the same, but pretty similar. And one thing you'll notice about your DNA is that it doesn't just randomly fall apart when it's in water, otherwise you would be dead. So this bond is actually fairly stable in water. It can last several days. Effectively, in terms of an enzyme's lifetime, that's permanent. Normally, the length of action for this enzyme is on the order of milliseconds, and you're talking about it being inactivated for days. That's a problem. So let's sort of zoom out to our zoomed out version of what's going on. Here's the neuromuscular junction. The acetylcholine's being pumped out here. Normally, our acetylcholine esterase will be degrading this at a rate of about 25,000 per second per enzyme. That's one of the fastest enzymes in our entire body. That's basically as fast as it could possibly do it. Each enzyme is degrading 25,000 acetylcholines per second. So each time a sarin comes in and blocks that, that's 25,000 acetylcholines that are building up every second. They can no longer be recycled. The choline's not going to get back in here. The acetylcholine can't actually get through the membrane by itself because it's really bulky and negatively charged. It's just going to build up in this neuronal cleft. And if you recall, what acetylcholine does is it activates the neuromuscular response. It contracts your muscles. So when it builds up and it can't be degraded, your muscles are just going to activate non-stop. In particular, your diaphragm is going to act up non-stop, and you're going to be choked to death, not going to be able to breathe, and you die. So yeah, that's why sarin is not good. Hope this helps. Thank you, and I hope you enjoyed the first episode of How Will This Kill Me?